derivative is and kind of teach you the shortcut rule right now. So f prime of x is going to be this. Or you can write it like this. So the way the rule works, this is called the power rule, and I'm going to have a bigger discussion about it tomorrow. The power rule states that if y equals x to the n power, the derivative, okay, the derivative will be this. Is your pencil not working? That's what the power rule says. So you move the exponent to the front. If it's granted, it's written in this format. It's just a plain old number, plain old letter x, raises some exponent, move to the front, drop it by 1. So that's what I did. I moved the 4/5 to the front, drop it by 1. Now, if you think about graphically what's happening here, or if you just do this, take the limit as x approaches 0 from the left of f prime of x, and take the limit as x approaches 0 from the right of f prime of x. If you think about it, you're doing a fifth root. What happens if you fifth root a negative number? Negative. And if you're doing the fifth root, if I'm doing 4/5 times the fifth root of negative 0.001, it's going to be super small negative, if that makes sense, right? I mean, kind of in a way. I mean, actually, I take it back. No, it's not. It's more. It's not gonna be super. It's gonna be like negative 0.01, I think, or negative point. I don't know. It's some weird number. But the bottom line is, you're doing 4 over a small number that's negative. If you're doing 4 over a small number that's negative, overall, what happens to the fraction? It's gonna be negative infinity. Yeah, it's gonna be negative infinity. I mean, if you want, if you don't believe me, you could just plug in a small negative number, a number approaching 0 from the left, like negative 0.000001. You're going to see that overall the fraction is going to get negative infinity or close to it, right? Likewise over here as well. It's somewhere in the middle. Graphically speaking, it looks like this also. This is the f prime graph, by the way. That's f prime graph. So yeah, we're definitely not differentiable. Mainly because f prime does not exist at what x value? Yeah, there you go. That's actually the main reason why. But I just wanted to explore graphically and numerically so you guys can understand better. Oh, that's the reason why. And when this happens, we talk about it. When your derivative is going towards negative infinity or positive infinity with the slope of the tangent lines, you're doing like this. What is it creating? A cusp. Yeah, that's cusp. So the type is a cusp. Notice I didn't graph the original function yet. But if you were to graph the original function, you would see that. Okay. So I didn't want to do the limit definition because it's not a fun problem to do. So I just did totally shortcut rule, which is probably advantageous because you get to derive more quickly. And then but then at that point, that's when I want to. Am I being analytical? 100% I am. I'm analyzing this derivative. As I'm analyzing it, what do I realize? Can I put 0 at the bottom? No. Therefore, I have answered my question. Or if I just think numerically, if I plug a number close to 0 from the left and from the right side, then if you're in positive infinity, there you go. It doesn't exist. Or if I look at graphically derivative, yeah, there's nothing happening here, 0. Fine. But more specifically, because going towards the left side, positive on the right side, or if it's flipped, whatever, that's a cusp. That's how we define a cusp. So that's how you can really break this down using calculus. Emma? No, it's okay. Correct. Correct. Because here's the original function does this. That's the original function. So if I drew tangent lines as I'm getting closer to the origin, the tangent lines are getting steeper. But on one side, it's getting steeper from a negative infinity perspective. On the right side, it's getting steeper on a positive infinity perspective. As they converge, I pretty much will have a vertical line here. So those vertical lines are undefined. The derivative expression proves that. Numerically, it proves that. And the graphical interpretation of the derivative proves that too. Okay, I think I broke that down as much as I could. So let's move on. Next up, let's show this is not differential x equals 0. State the type of non-differentiability. Okay, now this is looks a little complicated, like, well, whoa, root x squared, what do I do with that? But we've talked about this already. We built up to this. Root x squared is the same thing as saying what? Not quite. Close. Absolute value of x. Because it has to say positive, right? Because square roots never have negative outputs unless you put a negative out in front. Because remember, the function root x is always has a positive output, right? Always. So let's do it. F of x equals that. And I'm going to write a piecewise function because we can and we should. Why would I go 2x when x is what? And when x is bigger or less than 0? Yep. Yep, because it's like a graph, think about the graph. I guess, okay, I know that was a little bit of a confusing part. If you have absolute value, 2 times absolute value of x is a little steeper, right? But the right side is positive slope. So obviously I'm gonna go with positive x when x is bigger than 0. I'll go with negative x and it's left. And by the way, should 0 be included? Yeah, why not? Sure, good, yeah. I mean, sorry, yeah. Why should we include it? Yeah, correct. We don't have a x in the bottom, so you can put in either one. So if I clean up a tad more, when I clean up a tab more, it should look like this, right? 3x and negative x. So my graph is actually not that great. My graph could look better. My graph should be more like this, right? You guys would agree? Okay. So what's happening here, if I find my left-hand derivative and find my right-hand derivative, I should write this more formally, but I won't for now. Yeah, it's -1 here. And the right-hand derivative is 3 here. LHD does not equal to RHD. So not differential of x equals 0. And the reason is a corner. Because these are finite values, right? You may even want to state that somewhere. Because if they're infinite, then it would be a cusp or a vertical tangent. So you want to make that statement for corners. Right?
We could like see that it's continuous, but like,
Yeah.
do you want us to like write it down, like do the like?
Actually, yeah, I should have done that, right? Yeah, good point. Um, yeah, we just made a quick statement. Yeah, we should. Yeah, we should say it. Yeah. Thank you. That's being very thorough. I like that. Yeah. Um, continuity is okay, right? Yeah. I mean, what I would probably do is I'd probably lead you to. I'd probably say, "Hey, is this continuous?" So I'd probably do that. But you should state that. Yeah, that's a good idea. Try.
Oh, positive, it's going in different, also the negative.
Yeah. Yeah, it can also do this too. These are cusps. Like something like that, I think would be like x minus one raised to like the four-fifths power and a negative out in front. Because you could transform those also. That's a possibility. Um, and that would be still the same thing. Right? But it means that these are finite numbers, the one-side derivatives. They didn't have infinity. They actually had like finite numbers that we can identify. Yeah. Okay, questions? All right, let's keep moving. All right. Okay. So in general, most functions typically will be differentiable. Like polynomials are nice and smooth. No reason there would be any corners, right? Rational functions, except at the vertical asymptotes, right? But all the different parts of a rational function, like let's say I give you a really crazy rational function, like something like this here, and like have something like this and like that. We've seen rational functions like that, right? Each of those curves are nice and smooth still. I can find derivative at any point on each of those branches, but at the asymptotes are not. Trig, sine and cosine, they're fine, right? There's no issues with sine and cosine. There's no sharp corners with sine and cosine. Um, I mean, with the ones that have asymptotes like tangent, cotangent, cosine, and secant, sure, you have a bunch of places where they're not differentiable, but on each of the branches of curves, they're cool. Exponential functions, that's continuous. No issue there. Those should be, I don't see any corners. Logs, that's fine too. I mean, of course, log has a restricted domain, but so and any combination of that. If I said like x squared plus log base 2x or sine x minus 1 over x, those are fine too. Um, there'll be particular moments where we'll try to find that, but for the most part, those are differentiable. Okay, next up. Now we're going to talk about how to do this in the calculator. So this is where I want to get your calculators out. And you're also going to understand the algorithm the calculator uses, and you're going to also understand the calculator is not fully trustworthy. You'll understand that too, because the calculator will lie to you. And I'll tell you why. Some parts, yes, I do want you to. Because here's the other thing too. This is now becoming an AP Calculus AB class. So there are calculator skills you need to know. I need to teach that to you. And Ms. York would expect you guys to know that in a few months. So I do need to make sure you guys are comfortable doing the derivative in the calculator because there is a calculator portion to the AP. So let me pull up an app here. Who's singing? It's really nice singing. All right. Okay, TI A4. Here we go. Okay. Why am I getting an ad about that? That makes no sense.
Okay.
Okay. All right. So first question is asking us, many graph calc can approximate derivatives numerically with good accuracy at most points of their domains. In a TI-4 calculator, you can find the derivative function at a certain point by pressing math 8. So if you do hit math, what the heck? This free things. What? I don't want to play games. What the heck is going on here? These ads, so annoying. Okay. Oh, goodness. Okay. I don't know what's going on here. All right. Yeah, if you hit math 8 and deriv is right there. And the nice thing is with the newer operating system, it does all the symbolic stuff. So you can see it sets up like this here. And so the way it's what's asking is asking for d of something. It's asking for an expression, and it's asking for an x value. Let me move that because that's getting kind of annoying. Yeah. So what you could do is when ask you to find a derivative, you got to choose what variable you want to put in here. So I'll put x, I'll put x cubed, and I'll put x here as well. So you're always going to put x and x because you have to tell the calculator with respect to what variable. Because you can do derivative of multiple variables, by the way. You don't have to use the x. You can use any variable you want. But since we're doing things in terms of x, you have to calculate, no, hey, I'm taking the derivative with respect to x. And then you have to give the expression you're taking the derivative of, x cubed. But the problem is that this is not an algebraic computing system. So some of you guys might be familiar with the more advanced calculators like TI Inspire or some calculators that actually can give you expressions for derivatives. This calculator does not do that. You have to actually give it a number and it's going to evaluate the number for you. So it's like f prime of a, not f prime of x. This cannot do f prime of x. You can do f prime of a. And what was the x value we wanted to evaluate? 4. There we go. So we're going to punch that in. So I'm going to do d dx of x raised to the third power. And I know the derivative is 3x squared. So if I plug in 4, I should get 48. And I get 48. However, it doesn't give me 48 straight up. It gives me 48.000000001. What do you think is happening? Does anyone know? Okay, good for you. You're lucky. You're one of the unlucky ones. Mine did not. What do you think is happening? How can it's not? Why is mine not giving? Fine, every calculator is fine, but why is mine broken? Or why is mine not giving 48 straight up? What do you guys think? It's approximate. How do you think it's approximating? Oh, okay, good. All right. Well, let's talk about it. Okay, there we go. Let's talk about it. So it's approximating, right? By the way, there's another place you can do it as well. If you hit Alpha window has another some cool shortcuts. It does log, it does derivatives, it does some other stuff too. So that's another place you can identify. Back in the day, before they upgrade the calculators, um, if you ever are so inclined, if you're curious, you can actually turn off the new operating system and go back to the old operating system if you ever so care to do that. It's under a math printing switch to classic. You hit mode and go to classic. And then if I hit math, option 8, it writes as n deriv, which stands for numerical derivative. You'd actually have to write the function first. And notice it does it like this. And then you have to tell with respect to what letter. And then you have to put the number in like that. Why you'd want to do that? There are times where that actually can be advantageous. I can't think of the specific moment right now. When that time comes, I'll tell you guys. Sometimes that might be a good idea to do that. But just so you know, the default is math print, which is the more symbolic way of doing things. So just so you know. Um, you can choose what letter you want. You can do any letter you want. It's up to you. I just chose the X because we always use X. But it's totally up to you. Yeah. So it's actually between the slope using the limit definition of slope at a point. Well, not really. The answer is no. It's an approximation. Recall that the slope of secant 2 points are really close together when we approximate the slope of the tangent. Here's actually what it's doing. Here's what the calculus is doing. It's doing an approximation. I'll explain right now. It's doing this. It's doing f of 1.00. Sorry, it was 4. My apologies. It's doing f of x plus 0.001 minus f of x minus 0.001 over 0.002. That's what n deriv's doing. So why is it doing that? Because it's close enough, right? So if I look at x cubed, that's 3.999 That's 4.001. And 4 happens to be right in the middle. There you go. So it's close enough. It's good enough. That's what it's doing. So it's not going to be too deceptive. But is it being fully honest with you? No, but it's close enough. So it's doing a secant line. So this is really a secant line. That's very close to the tangent line. So that's what it's doing, in case you're curious. And actually, if I were to do that right now, actually, you guys might appreciate this. One thing that's also kind of good to do is to understand how to use other features in this calculator. So I stored y1 as x cubed. I'm not sure if you guys know this, but you guys can actually pull up y1 through y0, and you will need to do this on the AP exam. You will need to. So it's good we start the training now. Desmos has some features. I think it's not the best. I think it's better to know to use the calculator. So I could actually call up y1 and set up like f of x notation. So 4.001 minus alpha trace 3.999. Hit enter. Oh, you go to y equals and put it there. And then divide by 0.002. There you go. That's what the calculator did when it did end derivative. It did that. Um, and actually, Avery, I think I know why probably yours is doing that. You might have a setting where it's probably rounding. It could be. I could be wrong. I don't know. Or maybe yours is just cooler than mine. Y1 was x cubed. Oh, how you call it up? Hit alpha trace. Alpha trace. There's another place you can do 200 vars and then y vars and then function, but that's kind of a pain to kind of go through all those windows. I just go to the shortcut, do alpha trace. So you can do that. That's a pretty cool feature you could do. Now, another thing to be mindful about too, this will lie to you big time. Let's say I want to find the derivative of 1 over x at x equals 0. Well, I know it's undefined at x equals 0. Right? I know that. But here's what the calculus is going to tell me. It's going to say, now this is lying to you big time. It's telling the slope is 1 million. But at 1 over x at x equals 0, are we continuous at x equals 0 at 1 over x? So the derivative does not exist. It should tell me that. So someone's not really careful. But what is it doing? Now you know. It's doing the slope between what 2 points? If I'm at x equals 0, it's doing the slope a little bit higher than 0 and a little bit. So at 0.001 and negative 0.001. Of course I could do 1 over 0.001. What's 1 over 0.001? 1,000. What's 1 over negative 0.001? Negative 1,000. What is it doing? It's just find the slope between those 2 points. So it's doing this. That's why you can't trust this. It's not trustworthy. So you have to really look at it through a very skeptical lens. It's finding these 2 points here and connect those 2 points. Are those 2 points a very steep line? You bet. Is this a slope of a million? Yeah, it's probably a slope of a million. It is. Now, that's kind of like infinity, I suppose, but it doesn't really tell me really what's happening. That's so it's a little confusing. Um, so anyhow, something to keep in mind about that too. Okay, it's going to tell us more lies also. Right, but in order for us to represent an approximation to the actual slope, this function must be differentiable. Must be differentiable at that point. So absolute of x, right? I know what's going to happen. It's going to do this, which is going to wind up being 0.001 minus, what's after that negative 0.001? Just as positive counterpart, right? That's what it's going to tell you. It's going to tell you it's zero. So actually, I kind of did both part A and B for you guys. This is actually part B, by the way. Part A is actually doing the calculator. If I go back to the calculator again, alpha window, option 3, X, alpha window, option 1. That's what you could call up absolute value code math. Math and num is right there as well. X equals 0. It's going to say 0. But I know that's not true, right? Because I know absolute value is supposed to be this. Right? That's what's happening. So it's giving me that slope, which is like fine. That's the slope, but that's not true. What's happening because we know from a theoretical perspective, it's supposed to be does not exist, right? It's wrong. Yeah, this is not true because the LHD equals -1. It's a corner, right? Right. So again, it's lying to us. So I'll make sure you guys are aware of that. And analytically, you get the idea. Maybe that'd be good enough to state that. We get more formal about it. Like, yeah, I don't want to do that. Like, all the limit definition stuff. I think you get the idea now that, hey, this is a piecewise function. The slope of each piece is -1 and 1 on each side of the origin. Those are not the same. Hence, order does not exist. That's what we want to say. What was that? No, no, no. The quiz is on stuff from earlier. Like 2.4, 3.1, like, hey, here's like 1/x², find me the derivative of that. And then like with the curve sketching, like, oh, here's a f of x curve, graph me the slope of the, graph me the derivative. It'll be more like the notes actually. Like I might do like a cubic function and just graph it, like estimating the slopes. Being um it was like this on the notes. We remember we had this on the notes. And then you just estimated like the slopes at various points and then you just plotted the points and made your graph. That's all. Yeah, just like that. That's all.
Are we going to push after class ones?
At the end of class, sure.
Wait, so then we're gonna learn short kernel tie that. So it's the short kernel.
You can't use it. You can use it verify, but you have to show me the work. What was that? Yeah. Yeah. All right, let's keep going, guys. Um, so the conclusion here. Okay, formatting sucks. I apologize. The conclusion: numerical derivative works only when you know that a function is differentiable at a point. Okay, do not use it if you know it's not differentiable there. So let's take a look at natural log of x. That's a fun one. Okay. 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 So before we use a calculator to do this, and by the way, you actually could, there's a cheat code in the calculator. This is really huge for AP calculus, this cheat code. That will allow you to graph derivatives algebraically, like in terms of x. I'll show you that in a moment, how that works. Write fx natural log of x. Before we get too carried away, let's think about it. Oh, it's nice my next one. Okay, before we get too carried away, if I drew tangent lines, right? That's a very positive tangent line, right? Gets less positive, but does it ever get negative? No, it's always going to be rising slowly, right? It's never negative. There's nothing to the left of it. So the derivative does not exist when it's less than zero, right? Because you can't take natural log of negative numbers. That'd be weird. Because your base is positive, right? That can't happen. So you can't take natural log of negative numbers. That can't happen. But we expect some sort of positive slopes, okay. So here's a little cheat code you can do for graphing the derivative. You go to y equals, you type in your function, natural log of x. Actually, I didn't even have to even do that, but I felt like doing that. But it's okay. We'll do natural log of x for y1. Now here's what you do. Get alpha window, pick the derivative feature. That's the wrong one, sorry. Alpha window, there we go. D dx. Now I'm going to put y1 in the parentheses. So I'm going to alpha trace y1. Or you can type natural log of x. And this is what a lot of people don't know. You put x equals x. So I'm graphing the original function, just so I can see the original function. Then I'm graphing d dx of y1 of x equals x. What that's going to do, it's going to calculate the numerical derivative at a bunch of points in the window for this calculator. It's going to be very slow, but it's okay. But it's going to calculate a bunch of derivative values and make those y coordinates on y2. So when I graph it, there's the first one. Okay, well, because this is on a calculator, it comes out nice and clean. But you see the blue curve is the natural log graph. The red curve, what does the red curve look like to you? 1 over x. It looks like 1 over x, exactly. The red curve looks like 1 over x. That is actually the derivative of ln x. So it's going to be 1 over x when x is greater than 0 with a restricted domain. No, there's a formal proof for that. We're not going to do that until March. We will get there. Yeah. And because other skills I've not taught you guys yet, I need to teach you these skills before we get to that point. But I'm going to show you why it's 1 over x when we get. It's not powerful because it's a different function. It's not a monomial. For monomials only. Monomials. Well, polynomial, of course, if you have a bunch of polynomial terms, you do for each individual monomial, right? But there's still a lot of theory and other things that we haven't got to yet that we'll get there eventually. Just patience, yeah.
Wait, how do we find the derivative of like sine, cosine?
That's another thing too. We were going to do that too. We won't do that until end of February. We'll do that, and I'll teach you guys how to do that too. I mean, there's formulas for that we'll look at graphically, but then there's actually a derivation that goes with it. So, Okay, last thing, IVT or derivatives. One last theorem, then I feel comfortable that we've accomplished what we want to accomplish for today. IVT for derivatives. Okay. So we know what IVT is in general. We know that any y value in between two y values can be had as long as you're continuous, right? So we know this already. Like if a function f of x, if it's continuous on a closed interval, it takes on every value between f of a and f of b at least once, right? So now replace f of x with f prime of x. So a function f of x, or we'll say f prime of x, so a function f prime of x that is continuous on a closed interval takes on every value between f prime of a and f prime b. Now, if you want f prime, I know it sounds weird, but if you want the f prime graph to be continuous, it means f of x is differentiable for all the values between a and b. So if a and b are 2 points in an interval in which f is differentiable, that means that f prime is continuous. F prime graph is continuous on a to b. Then f prime could take on every value between f prime a and f prime b. Um, so for example, that's continuous for all real numbers. So let's say this is a and b here. And let's say a is 1 and b is 2. What's that prime 1 going to equal? What's that prime 2 going to equal? 2 and 4. So what this means is that can f prime equal 3 in an interval from 1 to 2? Sure. Because the slope is right now, my slope at f of a is going to be positive 2. Then my slope here is at positive 4. So slope of 2, slope of 4. So any slope between 2 and 4 can be half between a and b. Because in my differential in this interval, sure. I don't see any breaks in it. I don't see any corners or jagged edges, right? How nice is 2 and 4? That's great. So any slope between 2 and 4 can be had. That's what IVT for years is telling. Any slope, not any y value, but any slope can be had between 2 and 4. So to have a slope of 3.99 or 2.01, sure. Can I have a slope of 1 or 0? No. I can't have a slope of 0 between a and b because 0 is not between 2 and 4. Now, if I have a slope of 0, from -1 to 1, sure. Because I do have that flat line after working with vertex. So this can be helpful for discovering horizontal tangents in certain intervals if we need to find that. That can be helpful. Where you may want to deliberately find a negative slope, a positive slope. Because if you have a negative slope and a positive slope, can a zero slope be in between? Yeah, that's the practical purpose of IVT for derivatives. We could potentially do that. So yet another theorem here. So given a mystery function, here we go. F is differential interval containing -2 and 5. F negative 2 is this. Sorry, F prime negative 2 is this. F prime 5 is this, right? Will there be at least one x equals c value in the interval from -2 to 5 such that any of these three can happen? This, no, this, yes, and this, yes. That's because one, oh, is it one? I'm sorry. I thought I said -1. My apologies. My apologies. I thought I said -1. But they're all yes. They're all yes. And what key piece of information do you need? You need to know the interval and if f of x is differentiable on that interval. Okay. Now, what about part C? Maybe, but not a guarantee. It could happen. I mean, there's a lot of weird things that could potentially happen. Because what if like we're looking at a really wide range and there's all these like hills and valleys and all these like curving things happen? Maybe, maybe. But not a guarantee. But all those choices in A are a guarantee. Okay. And that pretty much covers this stuff. So this is good. We're definitely moving at a great pace here. So homework, let me figure out that's going to be. I think most likely I want you guys to do looking at handout C. Yeah, maybe 7, 8, maybe 9. We've not done shortcut rules, not quite yet. Maybe
No, I haven't.
I think this will be the rest of handout C. Let me think about it. I'll post this school later today. I'm surprised no IVT for derivatives. I think we'll just do 7 through 14. Yeah, I think that's what we'll do. All right. See you guys.